Next on the program is the concept of internal stability. So notice here the loop that we are considering with the set point signal. Previously we've denoted it R. The load disturbance, we had considered it as W, and dV, the output disturbance. Here N is measurement noise, right? So here in this course I should write C of SP, SP of SP, etc. But the concept here of internal stability is also valid for discrete time systems. We can write PV as a function of the different inputs SP, DL, dV, N, set point, load disturbance, output disturbance, and measurement noise. So this is how you have to read this. PV is this transfer function here acting on SP, this transfer function acting on DL, this transfer function acting on dV, and this transfer function acting on N. And then you have something similar for MV. As you can see, there are different types of transfer functions that are appearing. Okay, 1 over 1 plus BC, P over 1 plus BC, C over 1 plus BC, and PC over 1 plus BC. And you have sometimes the same transfer function but with a different sign, right? But you can see here that there are 4 types of transfer functions. And internal stability says that, well, the system is internally stable if all the transfer functions that you see over here are stable. You will see in the next 2 slides that this concept of internal stability will prevent so-called unstable pole zero cancellations. Note that you have to be able to reconstruct this transfer matrix over here and find the different transfer functions. By the way, this transfer matrix is valid in the case of a single input, single output system. I will show you again how you can find these transfer functions, and I will do it directly in the multivariable case so that these quantities will become transfer matrices, and you will see that you will have a different result than what you see over here. So this is only valid in this CISO case. Okay, so for instance, if we look at the relation between MV, okay, and SP, so this transfer function here, well, you put all the other inputs to 0, this one, and this one, and you can see here that, well, MV is C acting on SP minus PMV, right? So this is CSP minus CPMV, right? So we take this one on the other side. We have we are assuming here that we are in the multivariable case. You would have an identity matrix plus CP acting on MV is CSP, and MV is this matrix inverse. We are multiplying this equation by the inverse of this matrix over here, CSP. Okay, so in the multivariable case you would have something like this. Of course, you cannot interchange and replace CP by PC in the multivariable case. You can in the CISO case, and this is why this becomes C over 1 plus PC in the single input, single output case. Let us look at the relation between the load disturbance and PV, and again we'll do this in the multivariable case, and then we'll verify if this simplifies to this transfer function in the CISO case. Okay, so we're considering a load disturbance, so all the other inputs you can put to 0, and you obtain, well, PV is P acting on dl, right? Here you have a minus sign, minus C times PV. So we have P dl minus PC PV. We take it to the other side. We are in the multivariable case, so identity matrix plus PC acting on PV is P dl. So here PV is, well, this matrix inverse. Now we multiply this whole equation by this matrix inverse. So in the multivariable case, this is the relation that we have, and then we speak here of a transfer matrix. Notice here that the order is different than the one we had considered before. So in the CISO case, this will of course simplify to this transfer function as shown here on the slide. Well, let us first start with the situation where we cancel an unstable process pole. And what we'll do here is, well, write PS as BS over AS, right? And we'll do something similar here for the controller. We'll write it as CS over DS, right? Well, assume that there is an unstable pole in PS, then we can factor A of S like this, and we'll assume that this is the unstable pole. You can see this because, well, the pole is to the right of the imaginary axis. We'll assume now that we'll cancel this unstable pole by, between quotes, an unstable zero. We cannot say that this zero is producing instability, but what we mean is really here a zero that is to the right of the imaginary axis. You can see here that if you consider the loop gain PSCS, and we'll call this L of S, well, this one and this one will cancel out. This means that, for instance, well, because of this unstable pole zero cancellation, well, this S minus alpha will disappear from this transfer function from SP to PV, but it will not disappear from this transfer function because it will still be appearing in P. So let us compute this transfer function. By the way, this is the transfer function from the load disturbance to PV. So P over 1 plus PC is BS over S minus alpha A bar S, and then 1 plus, well, we have BS A bar S right here in this loop gain. Well, the S minus alpha has cancelled out, so we have C bar S over DS, right? If we multiply numerator and denominator by this quantity over here, what we'll obtain is BS DS, right? And then at the denominator we'll have the S minus alpha, and then we'll have A bar S DS plus BS C bar S, right? And this is here the denominator of the transfer function, and this is sometimes called the characteristic polynomial. You see here that S minus alpha remains a factor of the characteristic polynomial, so this transfer function here from the load disturbance to PV will be unstable. So it is forbidden to cancel an unstable pole of the process by an unstable zero of the controller, as this goes against internal stability. As you can see, this transfer function will be unstable. Well, we can now have a look at an unstable zero of the process that is cancelled by an unstable pole of the controller. Again, unstable zero between quotes, because this unstable zero will not generate instability. We just mean that the zero is to the right of the imaginary axis. So here again we have factored b of s like this, right? And s minus alpha gives an unstable zero between quotes, since, well, this zero is located to the right of the imaginary axis. And here we have designed a controller that cancels this unstable zero, because, well, s minus alpha appears here at the denominator of the controller. Okay, as you can see, s minus alpha will disappear from this transfer function, because it will disappear from the loop gain ps cs, right? And here in this transfer function there is only the loop gain that is appearing, but you can kind of see already that it will not disappear from this transfer function over here, right? So we can write this transfer function, and you will see that c over 1 plus bc is c of s, s minus alpha, d bar of s, and then over 1 plus, and here the s minus alpha will cancel out, so we'll have b bar of s over as, and then we'll have cs here over d bar s. If you put everything under the same denominator, you multiply by this quantity over here at numerator and denominator, this is what you'll obtain. cs a s divided by s minus alpha, and it's this one that is producing the problem, and then you'll have as d bar s plus b bar s cs, and this is again the denominator of this transfer function, and this is called the characteristic polynomial. Well, as you can see, s minus alpha is not disappearing from this characteristic polynomial, and you'll find it at the denominator of this transfer function. So this means that this transfer function, as alpha is to the right of the imaginary axis, will be unstable. So cancelling an, between quotes, unstable zero of the process by an unstable pole of the controller goes against internal stability. So this is forbidden, as this transfer function here will become unstable. When a pole or zero is cancelled, right, the associated mode, and the associated mode is exponential of alpha t, will not disappear. This is not problematic if the cancelled pole or zero is to the left of the imaginary axis, because this will go to zero. But if the cancelled pole or zero is to the right of the imaginary axis, so that the real part of alpha is larger than zero, then this mode will be growing. Okay, it is not disappearing, and it's growing, so it will cause instability. So this is why you should never cancel unstable poles or zeros, and this has implications further on in the course when we talk about feed forward, when we talk about internal model control, and when we talk about decoupling. Because feed-forward, internal model control, and decoupling will involve the inverse of the process, and there is a danger that you might cancel unstable poles or zeros. For your information, and this is only for students in control engineering, remember that we have seen from the course of state space control that one of the reasons why a system becomes unobservable or uncontrollable is that there are pole zero cancellations. If, for instance, the unstable zero between quotes of the process is cancelled by the unstable pole of the controller, the corresponding mode will become unobservable at the output. This is problematic because the mode will blow up and it will not be seen at the output. Of course, because the system is slightly nonlinear or because the cancellation is not perfect, after some time you will also see this state that is blowing up at the output. If an unstable pole of the process is cancelled by an unstable zero between quotes of the controller, the corresponding mode is becoming uncontrollable from the input. Okay, so the corresponding mode blows up, but you can do nothing about it with the controller. For your information only, but a pole zero cancellation is never exact. For a real system, you never know exactly where the pole or zero is located because your model is only an approximation of reality. So if the process has a pole, and here it's a pole in minus AP, and that you cancel it in the controller, this will be on the basis of a model. Okay, so this is the actual pole minus AP, and the actual zero will be minus AC. So AC here is really an estimate of AP, and in general it will be different than AP, right? So if you write the loop gain, this is what you obtain, and what you can do is the partial fraction expansion. You will see that A is given by this expression and B by this expression, and you can see that when AC and AP are equal, then obviously this one will be 0, this one will be 1, and you're left with 1 over SB, 1 over S plus B. But in practice, of course, your estimate of AP will be different to AP, so this one might be very small, but it's still there, right? So the cancellation is not exact, okay? And the cancelled mode, this one here, the cancelled mode is exponential of minus AP t, is still present because this one might be small, but it is still there. If this mode is unstable, this means AP here negative, this is problematic because even for a very small a, the unstable mode over here will become predominant after a while. And this means, of course, that since the pole zero cancellation is never exact, well, even transfer functions like PC over 1 plus BC will also be unstable. We will see that it is also not very wise to cancel slow poles of a process. The process that we'll consider is a first order system with delay, so Kp 1 over Ts plus 1 exponential of minus theta s, and you can see here that the gain is 1, the time constant 10, and the delay 1, so that we have 1 over 10s plus 1 exponential of minus s, right? And we'll use a PI controller. We haven't reviewed the PI controller, but the PI algorithm that we'll use and that will be introduced later is this one. So it's Kc, the gain of the controller, times E of P, right? This will be the proportional term. I'll come back to E of P later, and then plus 1 over Ti integral of the error, right? And the proportional error, this is how we call it, is B SP minus PV. We'll see later why we have a B here and what it can be used for. So this is the proportional error appearing in this proportional term, and the error over here is the classical control error that we've seen previously. It's SP minus PV. So on the integral action, it is the standard control error that is acting, and this integral action is going to make sure that PV is going to go to set point. So we'll consider here two PI controllers. This one with B is equal to 1, and this is the PI controller that you've seen in the previous course, Fundamentals of Control Theory, right? And we'll consider a second PI controller with B is equal to 0.5, so it will be a bit different. But also you see here that there is a difference in Ti, right? If we now look at PI controller 1, and you go to the Laplace domain, you remember that B is equal to 1 for this controller. Well, MV can be written as Kc, the gain of the controller, 1 plus 1 over Ti S times the control error. If B is equal to 1, the proportional error here is simply the control error, and this you can write as Kc TIS plus 1 over TIS, right? So with this first PI controller, since Ti is here equal to 10, what you have here is 5 10s plus 1 over 10s times the error. So what you can see over here is that there is a cancellation of the process pole, right? And this will not be the case for this second PI controller. And what we will see is that we will have a good tracking performance. Remember that tracking performance is related to the transfer function PC over 1 plus PC from set point to PV. But we will see that the load disturbance rejection will be slow, and this is related to the transfer function P over 1 plus PC, and this is from load disturbance to PV. You can see here that this pole will disappear from this transfer function, but it will still appear in this transfer function, and this is why the load disturbance rejection will be slow if this slow pole is cancelled in the controller. This is the control system configuration that is associated to controller PI1. Remember that this is the controller that we had found in the previous slide, right? PI1, and you can clearly see here that the pole that is stable over here is cancelled by the 0 of the controller. So here there's nothing that goes against internal stability because the cancelled pole is stable. But what will happen is that the stable mode associated to this pole, and this is the associated mode, will become uncontrollable as well. P is equal to minus 0.1 appears at the 0 of the controller, right? So if the mode appears or is excited by the load disturbance here. Since we have here a 0 in minus 0.1, will not be able to influence it, this mode appearing from the load disturbance, using the controller. And this stable mode will have to disappear naturally, slowly from the closed loop system, right? Another way to see this is that, well, this pole will disappear from the closed loop transfer function PC over 1 plus PC. This is the transfer function from SP to PV, but it will not disappear from the transfer function P over 1 plus PC, and that's the transfer function from DL to PV, right? And why is this? Well, here you have only the loop gain that is appearing in this transfer function. Here you have the loop gain, but you have the process itself. So in the denominator of this transfer function, you'll keep this factor, okay? So this slow pole will be kept in this transfer function. So if you do a simulation, you will obtain something like this. So here in brown, the set point, in green PV, MV here, the manipulated value in blue. You should always look also at the manipulated value, and here we have the load disturbance, right? In full line you have the responses with the first PI controller, and in dotted lines the response with the second controller. Remember that this controller is as follows: MV is KC, and then B set point minus PV, right? This is what I've called the proportional error, plus 1 over TI, right? Integral of set point minus PV dt, right? So for PI 1 we had KC is equal to 5, B is equal to 1, and TI is equal to 10 seconds. And for PI 2 we had also KC is equal to 5, B is equal to 0.5, and TI here is 3 seconds, right? You can see this effect of B here when the set point is changing, and this is what is called the P kick. This will be of course reviewed later on in the course, so maybe at some stage you'll have to come back to this example, but you can see here that when there's the set point change, there will be a P kick, and this P kick will be KC times B times the delta set point. This is the P kick, right? So in the first case it is a P kick of 25, and with B is equal to 0.5 we have a smaller proportional kick of 12.5. You can also see the difference between the controllers in this region where you have the delay. You can see here that for 1 second here, right, PV is not reacting, so the error is constant, so it's being integrated. Here you have TI is equal to 10 seconds, so you have a small slope, right? And here TI is 3 seconds, right? The slope is higher, okay? So remember that TI is entering here in the equation as 1 over TI, right? So we'll discuss this form of the PI controller later on in the course, and we'll discuss also why you would use such a parameter B. But you can see here that the set point response is given here, and well, that the first PI controller does a little bit better than the second PI controller. But when it comes to the load disturbance, you can clearly see that the first PI controller, because it cancels the slow pole, has problems rejecting the load disturbance. As you can see here, the load disturbance has to, well, disappear naturally with the time constant t. Okay, so it disappears roughly after, well, 3 to 5 times t, so around 30 to 50 seconds, right? Whereas this second PI controller, which does not cancel the slow pole, does a much better job at rejecting the load disturbance. So this technique, which consists in compensating a pole of the process that you see in many books, well, has advantages because it makes the calculations easier, but when it comes to load disturbances, this is clearly not a good technique. Before we start talking about the Bode diagram, I would like to recycle a slide that's coming from the course Signals and System. If a system h of s, this is the transfer function, is subjected to a sinusoidal input of this type, then you can compute the steady state response, and here the word steady state is really important. So this means that all transients have disappeared. The hidden assumption here is that this system is stable, otherwise the transients would not disappear. Well, this steady state response is a sinusoid at the same frequency, and this is coming from the fact that the system is linear, right? And you can see that this output sinusoid in steady state is amplified or attenuated, and that there is a phase shift, right? So this linear system acts as a frequency filter. If you vary the frequency omega from 0 to infinity, well, we obtain a whole lot of these responses, okay, that might be amplified and attenuated and phase shifted differently according to omega. And this is what is going to be represented graphically in the Bode diagram. So the magnitude plot on the top part of the Bode diagram is really the transfer function evaluated at s is equal to j omega, so it's considering the transfer function on the j omega axis, and then you subsequently take the modulus, right? And the phase shift is obtained by taking this same quantity and taking the argument of this complex number. The Bode plot, named after Hendrik Bode, has two parts. The top part is the Bode magnitude plot, and well, it is related to the magnitude or modulus of h of j omega, right? And usually it is magnitude expressed in decibels versus the log frequency, right? To obtain decibels, you have to use the 20 log rule, and here it's the base 10 logarithm that is used. The bottom part is the Bode phase plot, right? And it is related to the argument of h of j omega, right? And here the phase shift is plotted against the log frequency. And what is nice is that if you have a very complicated P of S, you can kind of decompose it in simpler components, P1 to Pn. And if you're able to draw the Bode diagrams of the individual components, then you simply have to add up. The phase shift adds up, and since we're working here with a magnitude in decibels, well, multiplying here will become a matter of adding distances in decibels, and this is because of this relation that is valid for the logarithm and also for the logarithm, of course, in base 10. This should not come as a surprise. This is a review of what you have seen in the course Fundamentals of Control Theory. Well, let us take an example. We can consider the first Bode diagram here in blue, and this process, let's call it P1S, is that of a pure delay e to the minus theta s here, and theta is equal here to 0.05, right? We'll see later that at the frequency 1 over theta, right, and this corresponds to 20 radians per second, the phase shift will be 1 radian, right? And 1 radian is around 57 degrees. You can see that in the magnitude Bode plot, of course, we have 0 dB at all frequencies. Of course, a delay is not changing the magnitude, okay? It has only an influence on the phase shift. If this is a surprise, this is not a problem. We'll review this later. In green, you should really recognize the Bode diagram of a first order system, right? And this first order system has a cutoff frequency that is, well, 1 radian per second. So 1 over the time constant is 1 radian per second. So this will be a first order system here with a gain of 1, right? Because in the low frequencies you have a static gain of 1. So we'll have here 1 over s plus 1, right? You can see here in the high frequencies the slope at minus 20 dBs per decade. Here at the cutoff frequency, an attenuation of minus 3 dBs, and in the high frequencies a phase shift of around minus 90 degrees. Again, if this is a problem, we'll review this. In orange, you have a third system, and this is also a first order system. You can see it, slope here, but the cutoff frequency here is 0.1 radians per second, so the time constant here is 10 seconds. So this is 1 over 10s plus 1. And then you can kind of imagine what the Bode diagram is of the system here in magenta, right? Well, the Bode diagram of the system in magenta is P of S, and this will be the product P1, P2, P3, and this is really a so-called van der Grinten system. And you can see here that the Bode diagram can be obtained by adding distances at all frequencies in the magnitude Bode plot, and you can do something similar with the phase shifts in the, well, phase shift Bode diagram. The Nyquist plot is named after Harry Nyquist, and it's a parametric plot of the frequency response. This means that the plot is a function of a parameter, and this parameter here is frequency. If you work in Cartesian coordinates, then you consider this complex number h of j omega as, well, written in Cartesian form. So it's the real part of h of j omega plus the imaginary part of h of j omega, right? The real part of the transfer function is plotted on the x-axis and the imaginary part is plotted on the y-axis, and we'll obtain a plot per frequency. Okay, each point corresponds to a given frequency. Well, here you view the complex number. Okay, this is h of s evaluated on the j omega axis as a complex number in Cartesian form. You can also work with polar coordinates, and then you can write this complex number as the module of j omega times the exponential of j times the argument of h of j omega. With this interpretation, well, the Nyquist plot replaces the two plots making up the Bode plot, so magnitude and phase, with a single plot depicting a rotating phasor. Here you can see an example of a Nyquist plot. You can see here the real part of j omega and the imaginary part of j omega. The values here in magenta are frequencies. Remember that this is a parametric plot where omega takes values from 0 to infinity. This is the value that corresponds to omega frequency is equal to 0, and this is of course in radians per second. So what we can now try to do is take a particular frequency, and we'll take this one here, so 0.1 radians per second, and look at the amplification, right, at the gain and at the phase shift. So we have to see this as a phasor, right, and this distance over here, the distance of the point to the origin, really is h of j omega in module for omega is equal to 0.1, right? So here we can read the gain of the system at the frequency 0.1 radians per second. This angle here represents the phase shift, so it's the argument of h of j omega at that same frequency, 0.1 radians per second. And in this, well, Nyquist plot, we can also have a look at the static gain, and here we see that at the 0 frequency, this corresponds to the static gain. Well, h of j omega is a real number, so there is no phase shift, and the gain here is equal to 3. We'll now review the concept of phase and gain margin. This is something that you've seen in the course Fundamentals of Control Theory, and what you should do to obtain the phase and gain margins, at least if you're doing it in the Bode plot, well, you should look at the Bode plot of the correct quantity, and the correct quantity is, well, the loop gain P times C. Why is this? Well, you've seen when we have considered internal stability that the transfer functions from all the inputs to outputs involved, well, a numerator, and this one is changing, but at the denominator you always have 1 plus PC, right? And what we are doing when we are looking at the phase and gain margins is looking how far the loop gain PC is from the point -1. -1 is the critical point, right? And this critical point -1 is characterized by a gain of 1, 0 dB, and a phase shift of -180 degrees. Well, we can now have a look at the phase margin, and to obtain the phase margin, well, you have to isolate the frequency where the loop gain as unit gain, so where the loop gain is 0 dB, and this is at this frequency here, omega c, and this is called the gain crossover frequency, or simply the crossover frequency. If we now look at the phase shift at this frequency omega c, well, this phase shift should be higher than minus 180 degrees. There should be some margin over here, and here this is the case. We can lower the phase curve and this will still be okay until we reach this point over here. So here we can see that there is a phase margin, and this phase margin really is 180 degrees plus the phase shift that you have at this crossover frequency. So it's 180 degrees plus the argument expressed here in degrees at the frequency omega c. Well, in order to obtain the gain margin, you have to look for the frequency where the phase shift is minus 180 degrees. So this is this frequency over here, and this is called the ultimate frequency. At this ultimate frequency, the loop gain should be, of course, smaller than 1. So the loop gain in dB should be negative, right? And here this is clearly the case, and here we have some gain margin. You can still lift up the loop gain, so increase the gain before you reach instability. And here this gain margin in dB, right? Well, it's approximately, let's say, 27 dB, right? So sometimes you just say gain margin in dB, you write it like this, or you're sometimes interested in the gain margin in absolute units. But you know that the gain margin in dB and the one in absolute units is linked by this equation, and this allows you to obtain the gain margin in absolute units. So in summary, you have to look at the loop gain. This is very important. I see sometimes students that consider P of S or C of S. No, it is the loop gain. Then you have to look at the frequency omega c, where the loop gain is 1 or 0 dB. This is called the gain crossover frequency. And you have to look for the ultimate frequency, the frequency at which the phase shift is minus 180 degrees. This is sometimes called also the phase crossover frequency. Well, the phase margin is 180 degrees plus the phase shift that you have at the crossover frequency. Indicative values are in between 30 degrees and 60 degrees. The more phase margin that you have, the more robust that you are to phase changes in the control loop. And of course, a phase change can be caused, for instance, by a delay in the system. The gain margin is 1 over the loop gain at the ultimate frequency, or the phase crossover frequency. If you multiply the loop gain by this gain margin at the ultimate frequency, you'll have a loop gain of 1. So you'll be at the limit of stability. So if you take something that is higher than this gain margin, you'll go to instability. Indicative values for the gain margin in absolute units, well, is the range 1.75, and if you use the gain margin in dB, well, you should use the range 5 to 14 dB. This is of course indicative. Remember that the link between the gain margin in absolute units, this is log 10 of course, and the gain margin in dB is given by this relation, but of course you can turn this formula around to obtain the gain margin in absolute units, and this is then 10 to the power gain margin in dB divided by 20. The gain margin is robustness to gain changes in the loop, in the control loop. And gain changes could come from the fact that maybe the process is non-linear, and around another working point the gain is different. It is also possible to find the phase and gain margins in the Nyquist plot. We can start with the phase margin, right? And for that we need to look at a point which corresponds to the crossover frequency. So that's a point where the magnitude of the loop gain is 1, and this is clearly where the Nyquist plot meets the unit circle. So this point here corresponds to omega is equal to omega c, right? And clearly the magnitude of the loop gain is 1. At that frequency, at the crossover frequency, you can see here that the phase shift is given by this angle. This means that we have some phase margin before we reach a phase shift of minus 180 degrees. So in the Nyquist plot, this is the phase margin. We can now look at the gain margin, and for this gain margin we need to find a point on the Nyquist plot that corresponds to the ultimate or phase crossover frequency, and that's a frequency where the phase shift is minus 180 degrees. So this point is where the Nyquist plot meets the negative real axis. So this point over here corresponds to omega is equal to omega u, the ultimate frequency, and you can clearly see that at that frequency the phase shift is minus 180 degrees. Well, the magnitude of the loop gain at the ultimate frequency is given over here, so the gain margin is 1 over this distance. Let us consider the Nyquist plots of a loop gain that is exactly the one that he had before up to this point, and here it starts to deviate and it goes like this before we meet the original curve again. You can see here that this new system has exactly the same phase and gain margin as the original system, but you can see here that the distance from the Nyquist plot to the point -1 is much smaller, so this system intuitively will be less robust. So the idea is to kind of take the minimum distance of the Nyquist plot to the point -1 as a robustness margin. This is what is shown over here in red. The radius that you see over here is the minimum distance from the Nyquist plot to the critical point -1, and we'll define ms, the peak sensitivity, as 1 over this radius. So when this distance becomes very small, the peak sensitivity is very high. We have seen in the previous slide that 1 over the sensitivity peak is the minimal distance between the critical point -1 and the Nyquist plot of the loop gain. So this is how you can rewrite this, right? So it's the minimum of the magnitude of 1 plus the loop gain, and it's a minimum over frequencies. The loop gain, of course, can be rewritten as PC, right? So what we'll do now is write ms. We're not interested in 1 over ms, we're interested in ms, the sensitivity peak or the peak sensitivity, and therefore we have to take a relation of 1 over x here and 1 over x, right? So the sensitivity peak can be defined as follows. But 1 over the minimum of this magnitude of 1 plus the loop gain is equivalent to taking the maximum of the magnitude of 1 over 1 plus the loop gain. If we now define the sensitivity function, and this is a transfer function, as 1 over 1 plus PC, right? And this is the transfer function from dV to PV, then we can kind of see why we call this the sensitivity peak. It is this quantity over here, so it is the maximum value of the magnitude of the sensitivity transfer function. Okay, so if you look at the Bode diagram of this sensitivity transfer function, well, it's the highest value in the magnitude Bode plot. This is also sometimes called the infinity norm of the sensitivity transfer function. This sensitivity peak is always higher or equal than 1. It should of course be as small as possible, but indicative values are the range 1.3 to 2. And we'll see that, well, the smaller the sensitivity peak, the more robust you are to the presence of sector nonlinearities in the control loop. So here we look at robustness margins, and we have a loop gain ls, that is ps c of s. So the control loop is ps c of s, right? And here we have the set point, here PV, and here is the feedback part. Okay, so we have a minus and here a plus. This is the error, and here we have MV here, and this is the loop gain. And the question that we ask is, well, are we robust to sector nonlinearities? Well, a sector nonlinearity is a nonlinearity that lies between two lines that are given over here. So the question is, can we introduce a nonlinearity in this control loop? And this is this nonlinearity, right? So that at the output here you have not MV but F of MV. And this could be the case maybe because we have, for instance, a control valve that does have nonlinear characteristics. What this shows over here is that if MS is very close to 1, so if MS is, well, more or less the smallest value that you can have, well, you can see here that this line will move to a vertical line, and this one will be a line with a slope of 0.5. So this sector will be very wide, and you can afford very wide sector nonlinearities in your control loop before you have instability. You can see here now that if the, well, peak sensitivity becomes very large, so MS tends to infinity, well, these two lines will come closer and closer to one another until you just have the line X over here, right? So you can see that the higher the peak sensitivity, well, the more problems you have with sector nonlinearities. So this peak sensitivity is indeed related to robustness to sector nonlinearities. Well, let us look at an example in MATLAB and determine the peak sensitivity. So we'll define the Laplace variable. This is done like this. We can now enter a process, and I will just enter a second order system. I will take a controller that is a controller with a TI of 8 and a gain of 2. If this is a problem, you can have a look at the section devoted to PID controls and look at this example later. And what we can then do is compute the closed loop transfer function from set point to PV, and here it is. And then we can, for instance, look at the closed loop step response with this process, and this is how it looks like, right? So this looks okay, and now we can have a look at the peak sensitivity. For that we need to construct the sensitivity transfer function. This is 1 over 1 plus PC. We need to have a look at the Bode diagram, right? And of course we need to take the Bode diagram of S, right? And then we can have a look at the sensitivity function, and here you can see that you have to look in the magnitude Bode plot of S, and the maximum is somewhere over here. Okay, so this looks like we have a maximum peak of 2.02 dB, so let's say 2 dBs. So if we want to obtain the value in absolute units, then it's 10 exponent of 2 dB divided by 20, and we have here a peak sensitivity of roughly 0.26.